Alright, so today we're going to be discussing the intermediate value theorem, which is a pretty big freaking deal. Intermediate value theorem, often referred to as the IVT, and kind of a big deal because here's your game. So you assume that your function f of x is continuous on some interval from a to b. It must be a closed interval from a to b. So how many different ways can you draw that? Well, let's see, only like a million. Okay, but here's a function, up to there. Okay? This guy right here is the point b f of b. This point, of course, is the point a f of a. Okay? And the idea is this, okay? Somewhere between a and b, somewhere along here, there is a value which we will call c. And when you get to that point, somewhere along here, you can say, well, look, I want to know some particular value. For instance, let's say this is 8. I want to know, can I show that that this function, for instance, has to cross 8? Well, yes. And the idea here is because I know that this function is continuous, and I know that initially the function was less than 8, and later on it was greater than 8. But because it's a continuous function, one of the definitions of continuous was what? Well, it has to be able to be drawn without lifting your pencil. That's the layman's version of it. So therefore it had to cross that line right there. So in other words, there has to be some value of c such that c, of course, is between a and b. Oops. Such that f of c is between f of a and f of b. Okay. Now, how do I care? Why do I know about that? Well, here's where it comes into play. If you see this graph, like so, right there, sure looks like there's a 0 right there. It sure does. And so I know that at f of 3 is positive, and at f of 2 it's negative, and this function's continuous. It's some kind of an x cubed minus 1 or something kind of a function, or something along those lines. I don't know what it is. Not 1 minus. Well, let's be honest, it'd be minus like 9 or something, but whatever, something like that. So the idea is when you graph that guy, it would again look something like this, and so somewhere between 2 and 3, you must have a 0. It has to cross the line y equals 0. It just has to. That is, it has to cross the x-axis. Now, when we do things like program calculators, now with Desmos it's not as big a deal, but in the old days it kind of, well, not even the old days, 5 years ago, back in the old days, we would do this in our TI 8384s. We'd graph this thing. We'd go, all right, y equals, and good grief, I'm in the wrong thing. Oh, brother. So maybe I put in like, I don't know, x cubed minus 9 or some such. No, that's terrible. Zoom 6. Nope. Zoom 6. Something along those lines. Whee! And clearly between 2 and 3 there is a 0. Not sure where it's at, but somewhere in that neighborhood. So back in the day we'd always go second calc. We'd go find a 0. And it would always say pick a number to the left of the value. Well, notice that your y value here is negative. So when I'm here at, like, say, for instance, 1.7, I've got a y that's negative right there. Okay, cool. And so I hit enter. And I want to go to the right-hand side of it. And I'll know I'm to the right of it because now my y is positive. And so it's looking between there, and it's going to keep guessing back and forth until it finds the value, which is 2.0800838, of course. And so the idea is that we can show that there has to be one there. Now, back in my day, like for instance on this one, you might put in f of, like I would use f of 2 personally. I'd get 8. And I'd first start off with 3, and I would say that it's 27. No. Well, clearly it's closer to 2 than it is to 27 because, for instance, what we're saying here is that the cube root of 9, right? We're trying to find that answer. Well, that's what we're actually trying to find, whereas a 0. So in this case, it's obviously closer to 8 than it is to 27. That just doesn't even make sense otherwise. I'm sorry. So let's back that up a train. If you put 3 into there, you get 27 minus 9, which is 18, which is what I meant. 8 minus 9 is negative 1. So we're closer to 2 than we are to 3 in this case. And that's what the picture showed on the graph over there, by the way. Okay, it's clearly closer to the 2 mark than it was to the 3 mark. Now, you could then say, well, what if I pick 2.5? I don't know. You could, I guess. So 2.5 cubed is, I have no idea. Get up there. No, try again, stupid. Clear. 2.5 cubed minus 9 is 6.625. Well, clearly that is still positive, so it has to be less than this. And back in the day, we were horrible people. We would torture children by making them do this until they found out where it would be. And so you'd tell, hey, 2.1 cubed minus 9 is, it's 0.261. Hey, that's really close. All right, then let's do 2.05. Yeah. And you could try to keep going back and forth, and eventually you'd hone in on it. That's all the calculator's doing. It's just doing it a heck of a lot faster than you can do it. Okay? Now, ooh, look at that. Negative 0.348 or something. That means that we must have a 0 between here and here. And again, we could keep kind of honing in on it. And the calculator said it was about 2.080008 or something. Well, that's probably good enough for me. But yeah, look where it's at. It's always hiding in between here. Okay? So we're doing these intermediate value theorem. That's the big deal that it's about. Now, the question might be then, well, for instance, can you show where a particular value happens? Well, probably. So for instance, if you had some other function like f of x is x squared plus 6x minus 1 or something, for instance, and I want you to prove to me that a 0 exists between don't peek, I'm going to graph this, between -8 and -4. Okay? So how do I do it? Well, first I need to establish, is this continuous? Okay? And of course it is, because it's a polynomial. So far so good. It's continuous everywhere. So then the question would be, what is f of -8? I don't know. That's 64 minus 48 minus 1, which would be 15. And f of -6 would be 36 minus 36 minus 1 would be -1. So because one of them is positive, one of them is negative, I'm guaranteed I got a 0 somewhere between them. Okay? So then here's my question. Where would that value exist? Well, in that case, I'd want to set it equal to the value in question. And then the value in question this time happens to be 0. Well, we know how to solve this. We could take the square. So the quadratic formula, for instance, you get 36 minus 4 times a times c is over 2. So it's -6 plus or minus the square root of 40 over 2. Square root of 40 is, I don't know. Let's get the calculator. Square root 40, 6.324. So notice -6 plus 6 is going to put me at 0.324 divided by 2, which is not helpful at all. I mean, I could find it, but I don't really care about that one. But the other one does make me a little excited. So, -6, oops. No. So -6 minus 6.324 divided by 2 is -6.12 or something. Okay? This is the value of c where that value occurs, and the value, of course, in this case is 0. Okay? And look, where is that? Negative 6.12? Look, it falls where? Somewhere in between there. What do you know about that? In other words, what we're saying is f of 6.12 negative, is equal to 0. Check it out. This falls in between here. This falls in between here. That's what we're saying. Okay. You know, you could do another one. Let's do another quadratic because they're easy. And I want to know, can you prove it equals 10 somewhere? I'm just going to leave it somewhere. Somewhere. Yeah, somewhere, by God, somewhere. Well, Mr. Green, what do you like to use? Well, I like to use 0 for one of my values. I think you're an idiot not to use 0. It's a wonderful number. Because what is f of 0? F of 0 is, well, it's negative 1. Okay? So now I need to find a value of x that gives me a value of y that's bigger than 10. 10. Why did you pick such a big one? Because I'm lazy. That's 100 plus 70 minus 1 is 169. Well, that's bigger than 10. So the number 10, the value of 10, which is a y value, falls in between here. Okay? So I'm guaranteed, come back here, you hippie. Because this is a continuous function, because it's, oh, you hippie, stop it. Because this is a continuous function, and because f of 0 is less than f of 10, and they're on either side of the y in question, I'm guaranteed it equals 10 somewhere in between there. Now you're like, well, couldn't I have gotten closer by just doing 2 maybe? Probably. That'd be 4 plus 14 is 18 minus 1 is 17. So somewhere between 0 and 2 it actually equals 10. So I could have just as easily done that. Okay? So then, again, how do I show where it equals? Well, that's just algebra 1 or algebra 2, I guess. So it's x squared plus 7x minus 11 equals 0. Again, obviously I could graph this. That's not the point. And I think we know who we're talking about here. I want you to see if you can actually do some, algebra and see how the pieces fit. I think that's important. Not because I think you're going to do it by hand always, but I just think it's nice to understand how the pieces fit. This is 93. Okay, and the square root of 93 is 9 point something. Oh, you hippie. Square root of 93, 9.6. I'm not interested in the negative one because that'd be negative 16 divided by 2, which isn't really, I don't care about that one. But I do care about the other one. So it's going to be 2.6 divided by 2, which is 1.8. This is the value of c, right? So if I do f of 1.8, what does that mean it equals? Well, it equals 10. And that is the long and short of how we use the intermediate value theorem. It's actually used in a few proofs later on in terms of how things work. Stuff that we'll pretty much just wave our hands at and go, isn't that neato? Oh, cool. We're not going to spend a great deal of time dealing with it. It's just something to talk about in that regard. And it'd be nice if I could tell you. So this is actually section 2.8. You'll notice that we skipped over 2.7. We're going to go back and do that. We'll do that one in class. I want to spend a little more time discussing that in class. And so that's what we're going to do with that guy. So, here's another example of one that you'll see on the homework. This one will sound a little weird at first when you first see it, but it's okay. So you want to show that the cosine of x is equal to the inverse cosine of x has a solution. In 0, 1. Okay? In other words, this thing needs to be equal to each other. So remember, another way to write this equation is cosine of x minus inverse cosine of x is equal to 0. And we can say, well, all right, here's our formula, like this, right? Yeah, it looks like a star. There we go. Q. So is this function continuous? That's the first thing. Well, cosine's continuous everywhere. Inverse cosine is continuous on his domain, and his domain is between here and here. So this is some aspect of this domain, so it is continuous. Therefore, the whole thing is continuous, at least on this box that we're interested in. Okay? So then the next solution is, well, let's put in 0. So if you do y of 0, you end up with the cosine of 0, which is 1. Inverse cosine of 0 is pi over 2. Right? Right. So that's negative, it's negative something. I don't know what that is. Well, it's negative. Yeah, I do too. That's a lie. It's negative 0.57-ish. Okay. Now, remember this. If you're doing this on your calculator, you're going to want to make sure you're in radians for this problem. Cosine of 1 radian, I don't know what that is. I kind of do. That's kind of a lie. Well, I know about what it is. But I'm going to ask Betsy just because, well, that's what I do. Make sure that I'm in the correct mode before I begin. Nope. So I'm going to take the cosine of 1 minus the inverse cosine of 1. And I get 0.54. Okay? Well, what's between those two? 0 is between those two. When I say has a solution, I mean, another way of saying that is when I write it like this, it equals 0. Okay? So somewhere between there, it obviously has a 0. So because this is continuous, because 1 is negative and 1 is positive, it has to have a 0 somewhere in between those guys. Yeah, that's all you had to show. Now another one that's similar but a little different, it freaks some children out, is this one. Show that 2 to the x plus 3 to the x equals 4 to the x has a solution. Where? I don't know. Well, you got to figure it out. So 2 to the x plus 3 to the x minus 4 to the x, okay, equals 0. But the idea here is this is my function of y. Okay? Is this continuous? Well, exponentials are continuous everywhere. So literally it's simply a matter of picking a value for a lower bound and a value for an upper bound, and such that 0 is between the two values. So this is A, this is B. As long as you can write this or it could be a decreasing function, that is A was bigger, doesn't make any difference to us. Okay, as long as you can show this to be true, we're good to go. So all I need to do, since I want it to equal 0, is show one of them is negative and one of them is positive, or vice versa, and we're good to go. Now, if it's me, I usually start at 0 because I'm lazy. I dig 0. That's kind of a nice thing. If you plug in 0, you're going to get what? You're going to get 1 plus 1 minus 1 is, it's 1. That's weird. So f of 0 is 1. So that's a positive one. Now, I could go further, but listen, let's see what's going to happen here. I don't think I have to go very far. Matter of fact, I think 2 is enough to get the job done, but I might be wrong. That's 4 plus 9 minus 16. That's negative 3. Nice. So f of 2 is negative 3. Therefore, because this is a continuous function, it's continuous everywhere, but at least it's continuous on the interval in question, but it's continuous everywhere. What I'm saying is that between here and here, I got these guys here. So because 0 lies in between these guys, because 0 lies in here, okay, there is a value that makes that happen. And where does that value occur? It happens somewhere on the x-axis between 0 and 2. And a person could graph that and actually see. I can do it a couple of ways. I think I'm going to do it 2 different ways. I'm going to go 2 to the x, and I'm going to do plus 3 to the x. Oops, no. Try again, stupid. No. There you go. And then I'm going to do 4 to the x, because what we're trying to say is we need to show that they're equal to one another. Hey, look what that happens. 1.57. Dog, isn't that between 0 and 2? Nice. Another way to write that, of course, would be to write that as a subtraction problem. So, like I did earlier, minus 4 to the x. Oh, dude. Booyah. 1.57. Okay? So that's what we're going to use the intermediate value theorem for. Really what it boils down to is it's another way to use the ideas of continuity, and we can do some pretty cool stuff with it later on. But not a very hard concept.